So it's almost like one-on-one tuition. So yeah, number one, let me just copy that one. Okay, so number one is, okay, how many moles of sodium atoms correspond to this many atoms of sodium? So sodium is Na, right?
Yeah.
And there are 1.56 times by 10 to the power of 21. So we know that 6.022 times by 10 to the power of 23 atoms correspond to 1 mole, right? Just bear in mind, this Avogadro's number does not have any unit, okay? So it's just the number of particles. So you can have atoms, or you can have, instead of atoms, you can have molecules. So whatever entity you're talking about, that becomes the unit, okay? So all you have to do is just use this formula. Number of moles is equal to the actual number divided by the Avogadro's number. So you just have to divide the actual number. Yeah. Question?
Oh no, not question. I was just had that answer. It's okay.
Okay. Yep. And you divide that by 6.022 times by 10 to the power of 23. Let me just decrease the volume a little bit. Yeah, that's all fine. And this is equal to, how much did you get?
I got 0.26 times 10 minus 2 moles.
Yeah, so must be something like that as well. Yeah, so 1.56 and 6.022 times by 10 to the power of 23. Then you get, yeah, something like that. Right?
Yeah.
So that's the answer for this one. Of course, if you have 3 significant figures and 4 significant figures, you need to go with 3 significant figures, okay? So 2.59 times by 10 to the power of minus 3, or 0.00, because there's 3 there, you have 3 zeros, and then 259, right?
Yes.
Yep, makes sense. All right, moving on. So this is in moles, okay? So I hope this one makes sense. Now there is another formula for number of moles, and number of moles is given by mass divided by molar mass, okay? So what does that mean by that? Of course, I think you guys know a little bit about this. So if you have 200 grams of water, well, we know that the molar mass of water is 18 grams per mole. And the reason for that, of course, is water is H2O, and it's made up of a 1 plus 1 plus 16 approximately, right? 1 is the molar mass of hydrogen, there are 2 of those, and 16 is the molar mass of oxygen. So you get 18 grams per mole. So if you have 1 mole of it, it'll weigh 18 grams. So if you have 200 grams, then just divide by 18. Then you get what? 200 divided by 18. Then you get about approximately 11 moles, right?
Yeah.
So something like that, okay? So that's another formula for number of moles. Now moving on to number 2. Number 2. Okay, how many moles of aluminium atoms are needed to combine with 1.58 mole of oxygen atoms to make aluminium oxide, Al2O3? So I'm just going to write, okay, so a chemical equation of, so Al, and then I'm just going to write O instead of O2. I'm just going to write, all right, 2Al, you can see 2Al, and then 3 oxygen make up this 1 molecule, right? So what I mean by that is you have 2 aluminium and 3 oxygen atoms combined to give one aluminium oxide molecule. So when they are all, so remember when you have a subscript, that means when you have subscript, that means you have, they're bonded together, right? When you have a coefficient, things like this one, that means they are all separate.
Yeah.
So you have two Al, so these atoms combine to give that molecule. So now the question is, so if I give you this question, so if I have 6 oxygen, how many aluminiums do I need? And how many aluminium trioxide do I get? Can you guys answer that question?
Sorry, I think my internet's connection's unstable. Could you just repeat what you want us to do?
Yeah. So if you have 6 oxygen,
Yep.
how many aluminium do you need?
Oh, okay. Yeah. Okay. Thank you.
The rule is internet connection also bad for me here?
No, it's fine.
Okay. You guys know the answer?
Is it 4 aluminium?
That's right, 4 aluminium, right?
Mm-hmm.
And that gives you what does that give us?
Al subscript 4.
Okay, the answer is actually Al2O3 times by 2.
Oh, yep. Okay.
Yeah. So you really can't change the way they bond. The way they bond is always with 2 aluminium and 3 oxygen. Mm-hmm.
Yeah.
So when you have 4 aluminium and 6 oxygen, you'll be producing. So if you have 4 of those, and 6 of those, then you'll be producing 2 of those. Make sense? So if you're doubling this one, then double this one and double this one, right? So that's how it all works. Now the question is, so this one is easy, 2, 3, 1. Therefore 4, 6, 2, right? But the question now is, if you have 1.58 oxygen, then how many aluminium? That's the question, okay? So I want you to think about that. So this is how you do it, okay? What you gotta do is 1.58 times by 2/3. So where did the 2/3 come from? Came from that, 2 and 3. Okay.
Right, the ratio.
Ratio, that's right. So the trick is, you got to divide. So you see how if I divide 6 by 3, what do I get? I get 2, right? And then times by 2 over here, then I get 4. So if you're wondering about this one, you divide this one by this one and then times by this one, then you get this one. Okay? So that's equal to 1.053. So was that right? 1.053 moles of aluminium. Now, can you work out also how many aluminium you get? So the ratio is 2, 3, 1. It's still Al2O3. You can't change that. So can you guys work out this one, please? So if the ratio is simple, 4, 6, if it's 4, then it's just double, 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 double. So that's really easy, right? However, when it comes to something like, all right, I've got 7 cheese, all right? How many sandwiches can I make with 7 cheese? And how many pieces of bread and how many pieces of apple do I need? So the rule is, you divide by your own coefficient, and then times by the coefficient of the value that you want, all right? So if you want to calculate the number of moles of number of pieces of bread, you first divide whatever you have by the coefficient of whatever you have, and times by the coefficient of whatever you want. Okay, so it's always up and then this way. All right, so 7 divided by 5 times by 3, and that gives me 4.2. That makes sense. So 3 to 5. So 3 to 5 is the same ratio as 4.2 to 7. Make sense?
Yeah.
So in a similar way, you do 7 divided by 5 times by 2. 7 divided by 5 times by 2. Then you get 2.8. You can also do 4.2, which you actually derive from 7, right? So you can actually do 4.2 divided by 3 times by 2. You still get the same answer, right? So that's 2.8 over here. So if you understood that, can you tell me how many sandwiches I get? So this is 2, 3, 5, 4. So maybe you don't have to use the technique because 2 and 4, that's just double, isn't it?
Right.
So you can just double this number.
Yeah.
Right? Or I want you to verify that this divided by this times by that is equal to the answer. Okay? Or that divided by that times by that, or that divided by that times by that. Okay? Can you guys work it out?
Yeah. I got 1.4.
Can't be 1.4, it's double.
No, okay, wait. When I times 2.8 by 2, which is
No,
the number.
2.8 divided by 2, isn't it?
Oh, right.
Yeah, divided by 2.
Yeah, I still get 1.4.
So if you divide this one by this, and then times by that.
Oh, sorry, yeah, 5.6.
Yeah, so I think it's just calculator error, isn't it? Yeah, so if you do that, you get 5.6, right?
Yeah.
Yeah, so if you guys understand that. Mihir, how are you going with this one? All good?
Yep. Yeah, I understand.
Pretty easy, right? Okay. Moving on to the next question. Okay. All right, number 3. Number 3 is how many moles of Al are in 2.16 moles of this? Okay. So we're going to establish the equation again. So with 2 Al atoms, 3 oxygen atoms combined together to give 1 aluminium oxide, right?
Right.
So if I have 2 molecules of that, so you guys need to know the difference between molecule and mole, right? Mole is the number that counts very, very big number. Molecule is just very small particle made of a few atoms, true? Examples are like H2O, NaOH, things like that, true? These are molecules. So 2 atoms combined with 3 oxygen to give 1 molecule, 1 aluminium oxide molecule. So if I have 2 of this, I'll get 6 of that and 4 of that, right?
Yeah.
But now if I have so 2 molecule will give 6 atoms and 4 atoms, right? Atoms of Al, 6 atoms of oxygen, 2 molecules of Al2O3. So I'm counting this whole thing as 1, okay? As 1. So I've got 2 of that. So the situation is a bit like, we saw this before. 4 of those, 6 of those, then you get 2 of those, right?
Yeah.
But now I can extend I can extend the word to moles. So if I have 2 moles, well, that's tremendously large number. You have hundreds and thousands of millions of billions of those, right?
Mm-hmm.
But because mole is a number, simple number, the ratio still applies. If you have 2 moles of this stuff, then you have 6 moles of these stuff, right?
Yeah.
Yep, 6 moles of those, right? And then you have 4 moles of Al, right?
Mm.
But you see the ratio still applies, 4:6:2. Doesn't matter what the unit is. It could be just molecules or moles,
Yeah.
So the question now is, if you have 2.16 moles, then how many moles of this and how many moles of that? Okay, so pretty simple. So it'll be slightly more than 4, slightly more than 6. I want you guys to work it out. Yeah, so you got to just do, the technique is you got to divide that one by 1 and then times by 3. But dividing by 1 is meaningless, right?
Yeah.
So just got to do 2.16 times by 3. Because, it's 2, 3, 1. So if you have 1 of that, you get 3 of that. And so it just times up by 3, then you get 6.48 moles, right? And double this one, then you get 4.32, true?
Yeah.
All good?
Yeah.
Yeah.
Yeah, moving on. Okay, so moving on to the next question. So here, it's a question on aluminium sulfate. All right, so aluminium sulfate is a compound used in sewage treatment plants. Construct a pair conversion factors that relate moles of aluminium to moles of sulfur for this compound. Okay. The correct way of writing this equation is actually, you guys know that aluminium is actually, when it becomes an ion, becomes Al3+. And there is sulfate. You guys have seen sulfate at school? The symbol from school?
Yeah.
So these are known as polyatomic ions. Have you heard of this term?
Yes.
Not quite?
Not in detail, no.
Okay, so I'm just going to give you some example. So it's very, very important. Polyatomic ions. Just going to Google that. Okay, so good example is this one right here. All right. Oh, the picture is very small. Sorry about that. Okay, that's better. So these are some of the common polyatomic ions that you will see. I think the one that you should definitely get yourself familiarized in year 11 is sulfate, hydroxide, nitrate. These things will show up all the time. And also carbonate. And I think acetate, that's very important for year 12. Okay, so these will be an ammonium. These will show up, I think, in year 11. The other ones, not so much, maybe in year 12. These ones will show up in year 12, I think. Chromate, so dichromate. And permanganate. I think phosphate is year 11. Okay. So polyatomic ions are formed when, usually when you have like sodium, then it's plus. That's a monoatomic ion, right? So just made up of one atom. When chlorine becomes an ion, becomes chlorine a minus. It's also monoatomic. So the reason for that is because, you know, sodium has like 1 electron outside, and that on the valence shell, and that goes away, and that turns into Na plus, and then electron minus. Electron is emitted. When you have chlorine, chlorine has a 1, 2, 3, 4, 5, 6, 7 electrons, and it gains an electron and then become chlorine with 8 electrons around it, and it becomes therefore negative. That makes sense, right? So these polyatomic ions is when, for example, I'll give you an example. Maybe hydroxide is the easiest. So hydroxide is, all right, oxygen has 1, 2, 3, 4, 5, 6, 7, 6 electrons around it. And hydrogen has 1 electron just outside, right? So in order for hydrogen to fill up its valence, it needs 1 extra electron. And also, oxygen requires 1 extra electron as well. So this extra electron came from somewhere else. So that becomes the, and oxygen is pretty happy because it's got 8 electrons now. So that can be done through introducing this outside electron, external electron. So this is the same thing as, you know, 2 electrons make up 1 bond. And you have this, and the whole thing is negative. So this structure here is known as Lewis diagram. Have you heard of Lewis diagram?
Yeah, we were.
So Lewis diagram is when you represent structure with all the electrons represented as dots. Anyway, so you see that more than 1 atom, so in this case 2 atoms came together and accepted some external electron somewhere from outside, and then forms a bond, and it forms an ion together, right? So that's why this is known as polyatomic ion. By the way, just coming back to this question again. Just put that aside there. So over here, we have sulfate and aluminium. And when you add them up, you need to have 3 of those. And the total charge for that is a 9 plus, right? Sorry, you need 2 of those. So in order for 3 plus and 2 minus to balance, this must become 6 plus and this must become 6 minus. So when you have 2 of those, the total charge will be 6 plus. And when you have 3 of those, so I'm going to represent it with, so we've got, so that's sulfate, SO4. That one there. So let's have 3 of those. And the total charge will be 6 plus, right? A 6 minus. And they form this big compound, which is, I can represent it as that, and then that, and that, and that. So that's a huge molecule, okay? Does that make sense to you?
Yeah.
2 of this and 3 of that combined. So this is equal to Al2. And then SO4 is repeated 3 times, right? So we have SO4 repeated 3 times. And there's no need for any charge because these 2 cancel out to become 0. So this is neutral, okay? So that's the proper way of writing the decomposition of this stuff. So Al3 plus, and then you have SO4 2 minus. You have 2 of this and 3 of that combined to give Al2 SO4 3. Okay, make sense?
Yeah.
So that's a proper way of doing this decomposition of the aluminum. Now, however, we don't care in this question. We don't care about the charges. We just care about their ratio, like how many sulfurs are there when there is this much oxygen, how many aluminiums are there when there is this much, whatever, you know. So let's take a look at the first question. Because we're only concerned about the numbers, we can just decompose them into this way. All right, so you have Al2SO43. We just write 2Al. Don't worry about the charges. And there's 3 S's, right? And then how many oxygens are there? There's 12 oxygen, true? Like that. Do you guys understand why there's 12 oxygen? Just let me know. I'll just interrupt any time if you want me to explain anything again.
Oh,
Otherwise,
no.
I'll just keep going. All right.
Sure. Yeah. All
You
good.
just have to keep giving me some feedback. Otherwise, I'll just be going on my own way.
No, that's
Yeah,
good.
just make things more difficult for you guys. Anyway, so this is the equation. So there's 3 sulfur and 12 oxygen. Okay, and now the question is, what is pair conversion factor that relate moles of aluminium, which is this one here, and the moles of sulfur? All right, so if I have, let's say, 5 aluminium, can you guys work out how many sulfur there are? Yeah, you guys can do that, right? So you guys learned the technique. Can you guys work it out just quickly?
So would it be 7.5?
Yeah, 7.5.
Yeah, 7.5. Just divide that one by that and times by this, right?
Mm-hmm.
So what you did was 5 times by 3 over 2. You divide by 2 and times by 3, right? Divide by 2 times by 3.
Yeah.
So that is known as the pair conversion factor. So the answer to this one is 3 sulfur over 2 aluminium. Make sense?
Yeah.
Yeah.
Or you can write 2 aluminium over 3 sulfur. Doesn't matter. But obviously, if you're going from here to here, then you got to use this one, right?
Yeah.
You got to times 5 by this one. If you're going from, if you've got, let's say 7 sulfur, then how many aluminiums are there? Then you got to divide by 3 and then times by 2. So that's times by 2 over 3. True. You start with 7 sulfur. The pair conversion factor is 2Al over 3S. And you see how the SS cancels out, and you just get left with the aluminium. That's another way. That's different perspective to this one. So you get 14 on 3 aluminium, which gives you about 4 point something. You know. Make sense?
Yeah.
Yeah.
4.3. Yeah. So that's 4.6 there. 4.666 moles. Okay. Were you guys able to understand this canceling out of the unit there?
Yeah.
Not really.
Not really. Okay. So let's go through a little bit on unit conversion. Okay, unit conversion is really important in both in physics and chemistry. So let's say you have, just very simple example, if you have 100 kilometers per hour. So let's say you're going to Sydney. You're driving and you're going at 100 kilometers per hour. Can you guys figure out approximately how many meters you go in 1 second? Can you sort of visualize and guess approximately how many meters do you think you go in 1 second if you're going at, you guys understand 100 kilometers per hour, right? You guys can feel that, true?
Yeah.
You guys know approximately how fast that is. So would it be all right if I say about 30 meters you go in 1 second?
Yeah.
Yeah?
Mm-hmm.
So how do we convert this one? So the answer is, you got to cancel this quantity. You got to have kilometer there and meter there. So the kilometer cancels out. So what is the pair conversion factor that goes over there? 1 kilometer is equal to 1,000 meters, true?
Right. Yeah.
Now you got
Yeah.
to cancel the hour. You're going to cancel the hour by having hour here.
Mm-hmm.
We know that 1 hour is 60 minutes, right?
Right.
1 hour same as, so that's the conversion factor.
Mm-hmm.
But then we don't want this to be in meters per minute. We want this to be meters per second, true? So you just got to cancel the minute as well.
Mm-hmm.
And then have second there. Then minute and minute cancels out. And we know that 1 minute is the same as 60 seconds.
Mm-hmm.
So the answer will be, so you're just left with the meter in seconds. Everything else is canceled, right?
Yeah.
So all you gotta do is times the 100 by 1,000 and then divide by 60. Okay, so 60s are at the bottom. So this is actually the same thing as 100 kilometers per hour times by 1,000 over 3,600. So it's effectively equal to just 100 times by 1 over 3.6, which is divided by 3.6. That's why they're saying in physics, if you learn physics, they say, oh, if you want to convert 100 kilometers per hour into meters per second, just divide by 3.6. That's what what teachers tell you, right?
Yeah.
That's the reason, okay? 27.7, okay?
Yep.
And that's in meters per second, right?
Mm-hmm.
So the technique that I told you before, if you have 5 Al, if the ratio is 2, 3, 12, 1, that's 2, 3, 12, 1. And you have 5 aluminium, if you want to know how many sulfur you need, how many oxygen you need, I told you to just divide by that times by this, right?
Mm-hmm.
Then you get 5 divided by 2 times by 3. So you get 7.5. Also, this one to this one is easy ratio, just times by 6 there. So you can also times by 6. 5 times by 6. That's 30. So there are pretty much 3 techniques, 3 ways of viewing it. So if you have 2, 3, 12, is it? 2, 3, 12. And then you have 5. And you want to figure out this and this. One way of doing it is divide and then times, right?
Yeah.
Oops. Hold on. Yeah, divide and times, which means 5 divided by 2 times by 3. 5 divided by 2 times by 12, right?
Mm-hmm.
So that's the technique. Second way is, if the ratio is really simple, like, going from here to here is difficult, right? Because we have to figure out how many times this one is to this one. But this one to this one is only just 6 times, right?
Mm-hmm.
So in that case, you don't have to divide in times. You can just go straight from there to there. This is times by 6 there. So times by 6 there, you get 30.
Yep. Yep.
And this one to this one is divided by 4. So you just divide this one by 4. Okay. Then you get 7.5. So if there is a simple integer multiple, then you just have to times. So that's another technique. So if you see that happening, then this is the most efficient way. But when it involves decimals, of course, number 2 never happens. Just got to use that technique, divide and times. Number 3 is just doing number 1, but it's just a different perspective. Okay, so this is the unit conversion method. So if you have 2, 3, 12, what that means is for every, just as, in this case, 1 kilometer is actually the same as 1,000 meters, true? And 1 hour is the same as 60 minutes. In the same way, we can say that This is oxygen, no, that's right, that's sulfur. We can say that 2 aluminium is equivalent or equal to 3S, but because for every 2 aluminium, it requires 3 sulfur to react, doesn't it?
Mm-hmm.
So in this case here, so we see that 2 aluminium and 3 sulfur and 12 oxygen is required to form 1 molecule. So in the same way, in the same sense, of course, this is actually a different concept to this one over here. 1 kilometer is exactly the same as 1,000 meter, but of course, like 1 aluminium, 2 aluminium atoms, it's not the same thing as 3 sulfur atoms, but we can say that they're equivalent when it comes to this particular reaction. That plus that give you that 1 molecule.
Mm-hmm.
So when you have 5 aluminium, then how many sulfur do we have? We can think of that as, all right, just flip that one. So it can have 3S is equivalent to 2Al. So times that by 2Al and then 3S, then you see Al cancel out. And you're left with 7.5S. S is remaining, right? Well, that's pretty much the same as 5 divided by 2 times by 3. But it's just a different perspective. It's from the perspective of unit conversion and canceling out. Okay, that's all. Yeah, all good?
Yeah.
So we just looked at 3 ways. Now moving on. Okay, moving on to next question. Oh yeah, we still didn't do this question. Okay, so here, I'm gonna write the equation again. So 2Al plus 3 sulfur, 12 oxygen, give you Al2SO4, 3. So the ratio is 2, 3, 12, 1. So A was about pair conversion factor between moles of aluminium and moles of sulfur. So that was just 2Al over 3S, or 3S over 2Al. Make sense?
Mm-hmm.
B, construct a pair conversion factor that relate to the moles of sulfur to the moles of this whole thing.
Yeah.
Okay, can you guys find out the ratio, the pair conversion factor of the sulfur and Al2SO4, 3? What's the answer? You guys a bit lost? So the answer for this one is very simple, right? So just 3 to 1. There are 3 sulfur and 1 aluminium. Now the next question is, if you have 0.9 sulfur, how many aluminiums are there?
I got 0.3. I don't think that's true.
I think it's supposed to be 0.6.
Oh.
All you got to do, so you have 0.9 sulfur, right? Divide that by that, times by that.
Oh, right, yes.
Then you get 0.6.
Okay.
Or if you're using the pair conversion factor, you times that by, so it's moles of sulfur, times that by the pair conversion factor. It's got to be S over here and aluminium over here. We know that 2 aluminium and 3 sulfur, that's the pair conversion factor from the equation, from the chemical equation, balanced chemical equation. So that's just times by 2 and 3, you get 0.6.
Okay.
All good?
Yep.
Next question is, how many moles of sulfur are in 1.16 mole of that? Again, the equation is this one over here. How many moles of sulfur are in 1.16 mole of Al2? So I'll give you some time for that. You see, if I have one mole of that, I get 2 of that, 3 of that, 12 of that, right?
Yep.
Now the question is, if I have 1.16 of those, 1.16 of that, then how many this, how many this, how many this? Well, they're specifically asking for this one over here.
Would that be 3.48?
3.48, exactly. Just this is a 1 to 3, so that's just times by 3, isn't it?
Yep.
So just got to times that by 3. What was it? So it didn't have to, you just divide by 1 and times by 3, right?
Yeah, so I just times it by 3, yep.
Yeah, or you can just times by 3, that's right. So you get 3.48, true?
Yep.
Yep.
You times by 12, then you get this one. Times by 2, then you get this one, okay? So that's the end of question 4. Not too difficult, right? Move on to number 5. Move on to number 5. We'll take a mini break at 10:15, okay?
Sure.
Sure.
Yeah. All right, next question is, how many moles of H2 and N2 can be formed by decomposition of ammonium, NH3? So the NH3, so a really simple way of decomposing that is just that and that, right? But like I said before, it's actually a little bit, if you're just concerned about the number of atoms, then you can do that. However, chemical equations, like for example, aluminium sulfate, when it actually decomposes, it decomposes into aluminium ion and sulfate, this polyatomic ion. So it doesn't split into individual particles where all of them are like neutral. So this doesn't really happen, but we could use that equation in the previous question simply because it was only concerning the number of atoms, right? But now, number 5 is a little bit more advanced. What this is saying is that when NH3 decomposes, it decomposes into, so it's actually, what it's saying is that H2, hydrogen usually exists as H2, right? It doesn't exist as H1.
Yeah.
And nitrogen also exists as N2. That these are gases that exist in our air as molecules. And that can combine to give NH3. So what that means is that 2 hydrogen, so that's 1 molecule, and it's together, you can see that, right? And nitrogen can give that. So can you guys first balance this equation, please? It can actually go both ways. If it goes that way, then it's formation of the ammonia. If it goes the other way, then it's decomposition of ammonia, okay? I'll give you some time. Can you guys balance this? So you put 2 there, 3 there, 1 there, right? Well, you don't have to put 1. That's just leave it like that.
Okay, yeah.
Then it's all balanced. So you cannot change what's in there, right? So that's already the way they exist. You can only change, all you can change is the number of these molecules. So if you have 1 of that and 3 of that,
Mhm.
then you can form 2 of that, right?
Yeah.
Does that make sense?
Mm-hmm.
Yeah.
Yeah, so let me just group them together. So that forms one of this, the other half forms that one, okay?
Mm-hmm.
So 3, 1, 2. So that's the way it is. So we're not going to be counting them as atoms. We're going to be counting them as molecules. These are all molecules, right?
Mm-hmm.
That's a molecule, nitrogen molecule, ammonia molecule.
Mm-hmm.
Now, the question now is, you got 0.145 ammonia. How many hydrogen atoms, molecules, and how many nitrogen molecules do you get? Okay, give that a go. Very nice. So, just got to do very simple. 0.14. Sorry, I just sneezed.
Oh, good. Bless you.
Yeah, but I'm muted, right? Yeah. So 0.145 divided by 2 times by 1. Then you get 0.0725. That's right, 0.0725. And this one would be that one times by 3, right? So I can just take that number and then times by 3. So 0.2175. So I trust that you guys all got these numbers.
Mm-hmm. Yep.
So if you have this many mole of ammonia and this many mole of N2 and this many mole of hydrogen. Okay. So what that means is you're not counting that one, that one, that one, that one, that one, that one individually. You're counting, okay, that's one, that's one, that's one, right? And that's one.
Right.
So that's the answer for the number of moles of hydrogen molecules. What about how many moles of hydrogen atoms are there? Then what you need to do is times this one by 2, right? Right? The reason is, inside of one hydrogen molecule, there are 2, right? It's a bit like there are 100 people. And how many eyes are there?
So 200.
200.
Mm-hmm.
It's a bit like that. So when you count 0.2175 mole of hydrogen 2, it's as if you're counting number of people. And when you're counting how many hydrogen atoms are there, but because they're inside of each hydrogen molecule, there are 2 hydrogen atoms, you got to times it by 2. Make sense?
Mm-hmm.
Yeah.
It'll be 0.435. Okay. Now, same goes for this one. How many atoms? How many nitrogen atoms are there? How many moles of nitrogen atoms are there? Just got to times by 2. And what about how many moles of? This is made up of 2 different atoms, right?
Yep.
Total 4 atoms. How many moles of atoms are there? Got times by 4. Okay.
Yep.
All right. Moving on to the next bit. Number 6. So we did this one yesterday, right?
Yes, we did that
Yeah.
one yesterday.
Mm-hmm. So you have 0.260. So we'll just actually write this one as like this: 6 carbon, because we're only concerned about total number of atoms. We just decompose them into individual atoms, okay?
Yeah.
Like that. And that gives you 1 glucose. Mm-hmm. So what you have is this is another way of doing it, 0.26 mole times by 6 times by 12 times by 6, right?
Mhm.
So you have 0.26 times by 6. Then you get 1.56. 1.56. And then times by 2, because it's double. 3.12. So if you add them all together, 3.12 plus 3.12, okay, then you get total 6.24 moles of atoms, right?
Mhm.
And then we have 6.24 moles of atoms times that by the Avogadro's number, because 1 mole is 6.022.
Yep.
That's atoms, right? So
Mhm.
atoms cancel out. Sorry. Per mole, sorry. So in 1 mole you have that many atoms, so moles and moles cancel out. So you get, what was the answer? 6.24 times by 6.022 times by 10 to the power of 23. So that was the answer. That's the number of atoms there.
Mhm.
Well, we also went through this. You have 0.26 mole. That gives you moles of glucose. You can first work out, you can times it by 6.022 times by 10 to the power of 23. Then you get the number of glucose. And then you times by 24. Because there are 24 atoms inside of glucose, right? You can do that, or you can times by 24. Then you get moles of atoms. And then you times by the Avogadro's number. So we talked about this stuff yesterday. So I'm not going to go through that again.
Mhm.
All right, moving on to the next question. So if you want to go through that again, just review the video that I'll send you later this afternoon.
Mhm.
Okay, now, from now it gets really easy. Okay, divide this. Yeah, this will be less confusing. Number 7, what is the mass of 1 mole of each of the following elements? Just need to look at the periodic table, right?
Yeah.
So they're just talking about the molar mass. Okay.
Mm.
Here, I've got the periodic table. Sodium is Na, and I can sort of see that this one is, hold on. Yeah, that's big enough. 22.99, right?
Mhm.
So 22.99 grams per mole, right? That's the molar
Yeah.
mass. And the symbol for that is Mr. So for A, Mr is 22.99 grams per mole. And then the formula is number of moles is equal to the mass divided by the molar mass. What they're looking for is the mass. So mass equals to the number of moles times by the molar mass. And you have 1 mole, right? So 1 mole times by the 22.99 grams per mole. And mole cancel out. So you just get 22.99 grams. I just did it in a more formal way. If the molar mass says, all right, there is 22.99 grams in a mole, how much does it weigh? If there's 1 mole, the answer is just 22.99, right? But I just wanted to use that formula just to illustrate. Now, sulfur. Just let me know if you have any question, okay? Sulfur is just under oxygen. That's that 32.06, right? So the answer is 32.06 grams. That's the answer. Chlorine. Chlorine is 35.45 grams. Make sense?
Yep.
That's the answer. Number 7, number 8. Determine the mass of the following. So let's talk about calcium phosphate. And of course, the reason for that is calcium is usually 2+ when it becomes ionized. And the phosphate is, if you go back to the polyatomic ions lists, you see 3-, right?
Mm-hmm.
So you need 2 of this, 3 of this and 2 of this. So just need to swap those 2 if you're lazy. And that'll form, so what that will do is 3 calcium 2+ balances with, electronically, with the 2 of the phosphate, true?
True.
Yeah, like that. And that becomes the calcium 3 phosphate. Now, let's work out the molar mass of the calcium phosphate. Calcium phosphate is, if we go back to the periodic table, calcium is 40.
Mm-hmm.
So all we have to do is 40.078 times by 3 plus. That's right. So you have 3 calcium.
Yep.
And then there's a 2 phosphate, right? 2 phosphorus, 2 P's.
Mm-hmm.
And then 8 oxygen, true?
Yeah.
Mm-hmm.
So P is 30.974. 30.974 times by how much?
2.
2, that's right. 2 plus. Oxygen is 15.999. 15.999 times by 8. And that gives us 310.174 grams per mole. So that's the molar mass. Now what they're saying is that there is 1.25 mole. All right, so the mass, you see mass is number of moles times by molar mass, right?
Mm-hmm.
So that's 310.174 times by, I'm just gonna do it the other way around. So that's 1.25 mole times by this much grams per mole. So mole cancel out. So that's the answer. Times this one by 1.25. Okay. So 387.72. 387. Okay, 3 sig fig. That's like 6 sig fig there.
Mm-hmm.
I would just like in chemistry, they don't really care. As you know, they don't. In physics, it's important that you take care of the significant figures.
Mm-hmm.
So that's in grams, right?
Yeah.
But if you want to be like really precise, then this is a 388 grams. Okay. So yeah, 1.25. That's 3 sig fig. The 6 sig fig. You can go only for 3 sig fig. Okay. Gotta round that up. So I'll give you this one as homework to you, number 8, because that's pretty simple, right?
Mm-hmm.
Number 9.
Oh, just afterwards, could you just send this lecture on the group chat? Thank you.
Yeah. Have I sent you the last night's lecture on the group chat?
No, I don't think so.
No. I did.
Oh, okay. My bad. Sorry.
Also with the homework question as well, with this
Yep.
these questions.
Yeah. Sure.
Good, number 9. We're going to do just one of them, okay? So we just want to know the number of moles. Number of moles is equal to the mass divided by the molar mass, right?
Mm-hmm.
Now, calcium carbonate, the molar mass. So sometimes we write like this, Mr with the bracket there. That means molar mass of calcium carbonate, okay?
Mm-hmm.
So if you count it, it's about 100 grams per mole. So let's take a look. Calcium is 40, right?
Yep.
40 plus. C is 12. Okay. And oxygen 3, so 16 times by 3. That's 100, right?
Mm-hmm.
1 calcium, 1 carbon, 3 oxygen. That's 100 grams per mole. Of course, you can do it with more decimal places, but I'm just for the sake of time, I'm just going to leave it like that.
Mm-hmm.
And therefore, what's the number of moles? Question A. Number of moles is equal to 21.5 gram, right? So that's a lot. That's like 5 times less than this one, right?
Mm-hmm.
So divide by 100 gram per mole. Now, what do you think about this? What's gram divided by gram per mole? The answer is mole.
Would just
right?
be mole.
Gram, gram cancel out. This
Mm-hmm.
one goes to the top.
Yep.
So that's why this and this cancel out, and you get the number of moles. And the answer is 0.215 moles.
Mm-hmm.
Okay. So I'll leave the other stuff to you, B, C, D. Now we're going to take about 5 to 10 minutes break.
Sure.
Mm-hmm.
And after that, we started at 9:15.
Mm-hmm.
So it's we'll finish at 11:30 if we take 10-minute break, right?
Yeah.
Mm-hmm.
Cool. So question 9 here says it's in milligrams, right? Just be careful with that. Because it's 6.98 milligrams. Hold on. What's going on? Oh, that's all fine. Yeah, 0.00698 grams. Just divide that by 1,000. Okay. That'll be in grams, and all you have to do is just find the molar mass of this substance here, and use that formula to figure out the number of moles. Now, moving on to question 10. It says, calculate percentage composition of this substance right here. Okay, so let's figure out the molar mass of this whole thing. So this is approximately 23 plus, sodium is 23, plus 2, that's from the 2 hydrogen there. And from phosphorus, phosphorus is about 31. Of course, you can do this more exactly, with all the decimal places. And 16 times by 4, then you get 23 plus 2 plus 31, 16 times by 4. You get 120. So 120 grams per mole, right? Now, percentage composition goes like this. So sodium weighs 23 out of 120, right? And hydrogen, there are 2 hydrogens, so it's 2. Each of them weighs 1 gram over 120, and just so on and so forth. Phosphorus is equal to 31 divided by 120, and oxygen is 48. Is that right? 40, no. So what's 16 times by 4? That's 40, 64, right?
Yeah.
64 divided by 120 there. So just calculate all these percentages. That's it. Okay. So 23 divided by 120. That's about 19.17%. 19.17%. 2 divided by, calculator crashed. Yep, 2 divided by 120. So that's 1.67%. And the 31 divided by 120. That's about 25.83. And 64 divided by 120. That's 53.3%. That's it. That's the percentage composition. So question 10BC, I'll leave that to you. These questions here, you can do the same and just check the answer at the back. We'll move on to, so nothing difficult about question 10 there. All good with question 10? Any question?
Yep. No, all good.
No,
Okay.
all good.
Now it gets a little bit difficult when it says it doesn't give you the exact formula, but it only gives you the percentage composition, and you have to find out, come up with a formula using those percentage compositions. So let's read the question. It says phencyclidine is a C17H25N. A sample suspected of being this illicit drug was found to have a percentage composition of 83.71, 10.42, and then 5.61. So if you add them up, do you get 100%? Let's double check. So 83.71 plus 10.42. 61. Yeah, pretty much 100%. All right, so what we need to do is figure out whether this compound that is suspected of being this illicit drug is indeed this illicit drug, okay? So what we need to do is just assume that there are 100 grams of this, of a C, X, H, Y, and Z. Then, of course, 83.71 gram will be carbon, and then 10.42 gram will be hydrogen, and then 5.61 gram will be nitrogen. So, how many moles does this correspond to, right? So we just divide 83.71, divide that by 12.01, okay? So what I did there is mass divided by the molar mass. That's 83.71 divided by 12.01. So that gives me about 6.97. All right. Now next one is, number of moles is, you go for 10.42, divide that by. So in this case, I cannot do this with rough numbers, because small decimal differences, they can lead to big difference later. 1.008, I get 10.337. So 10.337, so that's 1.008 there. 5.61 gram divided by nitrogen. Let's take a look. Nitrogen there, 14.007. So 5.61 divided by 14.007, that's 0.4. 0.4. And then 40051. Okay, 40051. Okay, so that's what I got. Moles. So I've got 6.972, 10.337 to 0.40051, and just need to check You see how this suspected, this illegal substance there has got 1 nitrogen? Well, right now we have 0.4 mole of nitrogen. So we got to sort of make this one into something to something to 1. Okay, so let's divide. What do we need to multiply by in order to get 1? So just divide 1 by the answer. It's about 2.5, all right. So if I multiply this one by 2.5, then I get 1. So let's apply that to every one of those. So 6.97 times by 2.5 is 17.4-ish. And 10.337 times by 2.5 gives me 25.8. So that's roughly similar to that, but this is close to 26, right? And this is not quite 17. So we did this work based on just making that one equal to 1, right?
Right.
Now, what I'm going to do is, instead of doing that, I'm going to make this one 17, okay? So we know that if I want to make that exactly 17, 17 divided by 6.97 is a 2 point, I got to multiply everything by 2.44, okay? So if I do 10.337 times by this one here, then I get very close to 25. So if I make that 17, if I make that the standard and make that exactly 17, this one will correspond to 25.21. Let's multiply this number by that number also. So 0.4005 times by 2.439. That's pretty close to 1, right?
Yep.
I think this reveals, so 0.97. So I could do it this way, and I could do it that way, you know? Or I could make that exactly 25. So it's really up to you.
Yeah.
Here I said that's the reference. Here I said that's the reference. I could also do the other one as well. But so if I look at that, it looks like it is indeed that illicit drug, isn't it? But if I look at that, I'm a bit, suspicious, is it really that illicit drug? So it's really judgment call. So if I check the answer for 11, it says it is consistent with the experimental result. So the theoretical is consistent with the experimental result, and therefore this is indeed that illicit drug. Okay. So I think they based it off this one here. Does everything make sense here?
Yeah.
Yeah. So it's just a tedious question. Now moving on to the next question. Okay, question 12. All right, how many grams of oxygen are combined with 7.14 times by 10 to the power 21 atoms of nitrogen in this compound? Okay. So let's first establish the chemical equation. I think they're just concerned about numbers. You see, they don't do, usually oxygen exists as O2, but they just wrote O there, oxygen, instead of O2, and also atoms of nitrogen. So I don't think you need to do this stuff, like that combined to give that. If you were to do that, of course, you can times this one by 2 and make that 4. So times by 2 here, and then times by 5 here. Then it's balanced, right? No need to do that. Just do N2O5 is from 2N and then 5O. So that's what we need to do, because we're just concerned about this and this. Now you have 7.14 times by 10 to the power 21 atoms of nitrogen. You need to get the number of moles of, there are several ways of doing it, but you can divide by the Avogadro's number. So I'll tell you what to do, okay? So divide by the number, Avogadro's number, and then you get the number of moles of nitrogen. So once you figure out the number of moles of nitrogen, because you see there's a 2 N and 5 O, then you can figure out, all right, you can figure out the number of moles of oxygen, just this number divided by 5 times by 2, right? Then you get the number of moles of oxygen. And then you got to times this one by the molar mass of the oxygen, which is 16. And then you get the number of moles of, the number of grams of oxygen, okay? Can you guys do it? So divide by the Avogadro's number first, and then you got to times this one by 215, and then times by 16. That's all you have to do.
Mm-hmm.
Okay, so I'll leave this one to you.
165.
0.061 gram, is it?
Yeah.
Approximately about that, okay?
Yeah.
So let's do it together. So you have 7.14 times by 10 to the power of 21.
Mm-hmm.
And divide that by bracket 6.022 times by 10 to the power of 23. Like I explained before, this bracket is crucial. If you're writing this in a line instead of fraction like that, you gotta have the bracket. So this is the number of moles of nitrogen, isn't it? 0.01185, 1186, like that. And then you gotta you have now, so this is 5 to 2, right? Don't worry about this bit here. So if you have 0.01186 and divide by 5 times by 2, so that's equal to just times by 2 and 5, times by 2 over 5. Then you get that equal to 0.00474. 0.00474. Now times that by 16. Then you get 0.07588. 0.07588. Okay, so let's double check the answer. So here's the question. So scrolling, this is question 1. Question number 12. 12 is 0.474 gram. So I think I made a mistake somewhere. There's N2, that's right, N2O5. That many grams of atoms. All right. How come I didn't get that number? So we'll check everything. So 7.14 times by 10 to the power of 21. That's right. And then divide that number by 6.022 times by 10 to the power of 23. That's correct. And then divide by 5 and then times by 2. That's right. And then times by oxygen. Oxygen is 16, isn't it? So I get that number. Did anyone get that number?
No.
Did you all get this number or not?
No, I got
Something else?
I got the 0.061 answer.
0.061.
Yeah.
But do you understand this method right here? Did you follow the calculation that I did? I think this is wrong answer.
Okay. Yeah.
Maybe how did they get that? So that's like about 10 times more. N2, 2 nitrogen, oxygen, okay, the compound of that. If you have that many atoms of that. Oh, sorry, I had to do that's nitrogen. Sorry, yeah, I think my bad. You have to times by 5 on 2, but it out to 2 on 5.
Oh.
because that's the number of moles of nitrogen. So you got to divide by 2 and then times by 5, right? So there you see that there is about 2.5 times more oxygen. So number of moles of the oxygen must be more. So this was wrong, sorry. So, yeah, I double checked it, but still I thought it was the other way around. So times it by 5, divide by 2 times by 5. Okay. Then you get that as your number of moles of oxygen. So it's about 2.5 times more than this one.
Yep, I've got
and then times by 16. 0.4744. 0.474 grams. Okay. So give you a little bit of map. This is known as mass-to-mass stoichiometry. So this is mass of substance B. This is number of moles of B. Number of moles of A. This is mass of A. All right. So this is known as mass to mass stoichiometry. So I'll give you an example. It's a slightly, quite similar to what we did over here. We'll come back to this in a minute. So what is mass to mass stoichiometry? So if you have like hydrogen, nitrogen combined to give ammonia. We know this is 2 and that's 3. All right, so if I say I've got 4 moles of hydrogen, then how many moles of nitrogen do I need and how many moles of ammonia will I produce? Can you guys give it a go? So it's just all about the ratio 3, 1, 2, right?
Mm-hmm.
So you got to do 4 divided by 3 times by 1. Then you get 1.33 there.
Yep, that's what I got.
Of N2. And just that's 1 to 2, so just double that. That's fine. That's 2.67. Like that. Now, so what we're doing there is just going from this to this. Like going from there to there. Okay. Now what I'm going to do is I'm going to say I've got 40 grams of hydrogen. How many grams of nitrogen do I need? So I'm going to change that to H2, mass of H2. Nitrogen is, that's number of moles of H2. That's nitrogen N2. And this is N2. Of course, you can extend it to number of moles of ammonia and the mass of ammonia. So you see, the mass is not going to directly correspond, right?
Yeah.
So if I have 6 moles, then I'll have 3 moles. Then I'll have, sorry, that's 3, that's 2 moles there. And then 3 moles, sorry, that's 4 moles there. So 6, 2, 4, that's 3, 1, 2, same ratio, right?
Yeah.
But if I have 3 grams of hydrogen, that's not going to give me, that's not going to require 1 gram of this and 2 grams of that, because different molecules weigh differently. They have different molar masses, right? So now the question is, it's very simple stuff. It's just have 40 grams. Now what we need to do, we know that just got to figure out how many hydrogen molecules are there, all right? So we know this relationship. So number of moles is equal to mass divided by the molar mass, right? So I just got to do 40 grams divided by the molar mass of hydrogen. So in this case, you have to divide by 2. Because we're not talking about how many hydrogen atoms are there. We're talking about how many hydrogen molecules are there. So you have to count that as, that's 2 grams per mole. So what you're going to get is 20 moles. Make sense?
Mm-hmm.
And then you have, all right, by the ratio, that's 3, 1, 2. So divide that by 3, then you get 6.67 moles, right? And then divide that by 2, then you get, divide that by 3 and then times by 2. That's equal to 13.3, I guess. So bring the calculator over here. So 20 divided by 3, that's 6.66, that's right. And then 20 divided by 3 and then times by 2. It's 2 and 3. That's 13.3, right?
Yep.
Now the question is, if I use 40 grams of hydrogen, how many grams of nitrogen do I need? And how many grams of ammonia is produced? Okay, so that's the question. So, all right, you go up this way, and you figure out the mass. Mass is equal to number of moles times by the molar mass, right? So what you got to do is times the 6.67 times by nitrogen's molar mass is 28. Each of them is 14. So you get 186 grams. 0.8 grams. So that's how much mass you need. Of course, there is no relationship between those two. There's no doesn't obey this simple rule 3. See, this is 3, 1.
Mm-hmm.
That's 3, 1. But then this is much bigger mass than this one, right?
Right.
And then you multiply this y here. So that's times by nitrogen, the 17. Ammonia is 17, so you times by 17 grams per mole. So 17 times by 13.33. So you get 226.61 grams. Okay. So this is known as mass to mass stoichiometry. Going from mass to mass. Okay.
Yep.
Make sense?
Mm-hmm.
So this is the most fundamental, the most fundamental quantitative chemistry skill that's needed before you move on to more advanced topics like rate of reaction, equilibrium, oxidation reduction, acids and bases. They all require this technique.
Mm-hmm.
Like throughout year 11 and year 12, you'll be constantly moving back and forth between grams and moles, grams and moles, grams and moles, okay?
Mm-hmm.
Yeah. And you'll be also going back and forth between volume to mole or gas to moles. So I'll give you all the map. So you have mass to the number of moles. You have mass to the number of moles. So in this case, this map is only concerning 2 items, okay? Now, this is the volume of gas. This is volume of gas here. And this is so this is solid, this is liquid, this is gas, okay?
Mm-hmm.
You see how number of moles is at the center of everything? So this side is substance A, this side is substance B.
Yep.
What's involved here in this bridge is molar mass. So if you go down this way, then you divide by molar mass. If you go up this way, you times by molar mass.
Mm-hmm.
Here, what's involved is molar volume. So we'll talk about that later.
Mm-hmm.
Next time, maybe tomorrow, I don't know. there's actually a bridge here and there as well. But we'll talk about that later. So what I mean by that actually is, let's say you have, actually we'll come back to that later. Here is volume, that's liquid, so this is in like mils or liters. And what's involved in this bridge is concentration.
Yep.
Okay, so we have the number of moles is equal to mass divided by molar mass. Number of moles is equal to concentration times our volume. And then the number of moles is equal to volume divided by the molar volume, okay?
Yep.
So these are the three equations that's involved in here. Now, before we move any further with this one, we'll come back to this one over here. So it's a bit like, so question 12, we'll try that again. So this question is not like any of those equations here. So maybe what I can do with that is maybe add another layer there. So this is number of atoms. And this is number of atoms, okay? No, or number of molecules. So let me just copy that diagram and give you this map. So what we are doing is we are starting with number of atoms of nitrogen. So we've got 2n plus 5 oxygen give you N2O5. What they are asking us to do is start from there. This is number of atoms.
Yeah.
So capital N stands for the total number, right? Of atoms or molecules.
Yeah.
Start from there and end up over here. You see? What is the number of grams of oxygen that combines with this many atoms of nitrogen? So you got to go there to there, and then there to there, and then there to there.
Yep.
See? That's exactly what we did.
Mm-hmm.
Another way of doing this is going, so one way of doing it is go there, and there, and then there. Another way of doing this is you go there, and then there, and then there. All right?
Mm-hmm.
So the first method, what we did here, is exactly the number one. Sorry. Yeah, so that's the first method. So we started with the number of atoms of nitrogen, right?
Yeah.
And then what's involved there is the Avogadro's number. So that's Na. So divide by the Na, then you get the number of moles of the nitrogen. So if you go from there to there, then you multiply by the conversion factor. So you got to divide by 2 and then times by 5, right?
Yeah.
Okay, is that too much to comprehend?
No.
It's all good? So
yeah.
Times by 5 and 2, that's what we did. So you went from there to there. Okay.
Yeah.
Then you get the number of moles of the oxygen, right?
Yeah.
And then you go up by multiplying by the molar mass. So we'll talk about number 2. So how do we go from, all right, so we have a 7.14 times by 10 to the power of 21 atoms of nitrogen. Then how many atoms of oxygen must be there? All right, the ratio still applies. If you're ever going from this side to the other side, you have to apply that pair conversion method. So you see, going from there to there. So going from there to there is times by how much? 5 and 2, right?
Yeah.
So you got to do also 5 and 2. Okay. There are, so if you look at this equation, there are always 2.5 times more oxygen than nitrogen, true?
Yeah.
So multiply 7.14 times by 10 to the power of 21 times what, 2.5. Then you get 1.7, yep, that number. Just copy that. So you get that many atoms of oxygen. Next step is figure out the number of moles. Just divide that number by Avogadro's number. So divide that by 6.022 times about 10 to the power of 23. Do that, and you get this many moles of, and that's exactly the same number as this one, isn't it? Moles of oxygen. You need to times that by 16 to go up this way. That's a 0.474. 0.474 grams of oxygen, okay?
Mm-hmm.
So we'll be keep using this map, all right? So you'll see. Okay, moving on to the next question. Okay. We've got 10 minutes. I'm just thinking about which question we should do. Yeah, we did 12. Let's just move on to question 13, just in the order, numerical order. All right, so we've got question 13 here. Quantitative analysis of a sample of sodium pertechnetate with a mass of 0.896 gram found that, so that's the formula. We don't know what X is, we don't know what Y is, we don't know what Z is.
Mm-hmm.
So we have 0.896 gram of this, but then 0.111 gram is sodium. And 0.477 gram is technetium. And the other one is oxygen. So let's find out the mass of oxygen. So this is the total mass, 0.896 minus 0.111 minus 0.477. Then you get this much, which is 0.308. Okay. Now let's divide each mass by the molar mass. Molar mass of sodium, molar mass of technetium, molar mass of oxygen. So Mihar, you do this one, and Soumya, you can do this one. I'll do this one, okay?
Mm-hmm.
So sodium is 22.99, sorry. Oxygen is 15.999. And the technetium, where's TC? It's a little bit warm in here. Okay. Technetium is, I can't find it. There you go. It's 98.
Sorry, sodium was 22.99. Just
Yep,
on
22.99.
I've got my answer. I've got 0.0048 as mine.
Mm-hmm. I've got 0.00487.
Mm-hmm.
0.00487. So very similar to your number there.
Mm-hmm.
And then you have Mihar, what'd you get?
Oh wait, was I supposed to do sodium or
Oxygen.
Oh, okay, sorry, I was doing.
That's okay. So this one over here is the answer for that one. 0.01925.
Yeah.
Maybe
That's
I
what
told
I
you to
got.
do that one. I don't know. I forgot.
Oh, that's okay.
Right, so that's the, so what we did here is, what they're saying is that the total mass of the sample is this much, and it was found that that much is sodium, that much is technetium, that much is oxygen. So we're just trying to figure out what the number of moles are for each of them, okay? We need to know exactly how many there are instead of their mass. We need that to figure out the ratio between them, okay? So you see how sodium, technetium, like if you have sodium, technetium, and oxygen, if that's all 1, 1, 1, then of course all of these numbers must be the same, right?
Yeah.
Yeah.
There'll be the same number of sodium, same number of technetium, same number of oxygen. But obviously I think it's gonna be, this and this are pretty much the same, I think.
Mm-hmm.
And this one is like 5 times them, isn't it?
Yeah.
By the way, so if I do get the more decimal places for this, 4.483. So there's another digit there, 3. So let's just divide. Let's just make that as the reference and divide everything by that number. Okay.
Sure.
Then the sodium will become 1, right? And technetium will become, all right, so that's going to be 487 divided by 483, right? That's 1.008. If you're wondering what I did there, I just ignored all these decimals because they're the same place. You can just do 487 divided by 483. And I can do, that's one more digit there, so I can do 1,925 divided by 483. So that's approximately 4. So I'm guessing the formula for this one is NaTCO4. Okay?
Mm-hmm.
So that's the answer.
Yeah.
Now, obviously, the formula could actually be Na2TC2O8, right?
Yeah.
They will also have the same ratio because, you know, we only worked out. Do you guys all know what empirical formula is?
No.
Empirical formula means experimental formula. So for example, we talked about glucose, right? C6H12O6. And the empirical formula for that is CH2O. I'll tell you the reason why. Let's figure out the percentage composition of carbon and hydrogen and oxygen there, okay? So carbon, hydrogen, oxygen. All right, so that's 12 times by 6 plus 12 plus 6 times by 16. So the mass of that is 180. And the percentage composition of carbon is 12 times by 16. 12 times by 6. So 72 divided by 180. So that's 40%.
Mm-hmm.
So 72 grams divided by 180 total. That's 40%. Now hydrogen is 12. Mass of hydrogen is 1. So just and there are 12 of those. So 12 divided by 180. Then you get 0. So it's about 6%, isn't it?
Yeah.
6.67%. Now oxygen is 16 times by 6 there and divided by 180, and that's about 53.3%. And if you add it all up, you get 100%, right?
Yeah.
Now let's talk about this one over here, carbon, hydrogen, oxygen. So the total mass of that molecule is, that's just the 12 plus 2 plus 16, right? So that's 30. So it's 12 over 30. That's 40% still. And then 2 over 30. That's the same thing. And then you get 16 over 30. You get 53.3%, right? So you get exactly the same percentage for this molecule. But when you have some unknown molecule, and that generates, and all you can tell, so you push this, you put this molecule into some machine, and the machine like grinds this molecule and then give you what they give you, what the machine gives you is that the percentage composition is this. This is what the machine tells you, okay?
Mm-hmm.
It tells you, all right, carbon, it's made this, whatever this unknown substance is 40% carbon and 6.6% hydrogen and 53.3% oxygen. But how do you know whether the molecule is this one or this one?
Right.
Or something else, you know, it could be C2H4O2, it could be C3H6 and then O3, all sorts of things, you know?
Yeah.
They all have the same percentage composition. So that's why what they are saying is just get the empirical formula, which means that when you get something like that, you don't know whether it's going to be this one or this one or this one. So just write that one. That's the empirical formula. So empirical formula is the lowest possible, the empirical formula is with the lowest possible integer ratio.
Yeah.
Okay?
Okay.
So if you have, for example, like C7, H15, O8, that's the empirical formula. So if you divide that by 7 or 15 or 8, you can't reduce any further. You can't divide by 2, you can't divide by 3, you can't divide all of them, you know? But if you have like C2H8O6, then you can reduce down. You can divide everything by the same number, right? Divide by 2, then you get this, and then this, and then this one, right?
Yeah.
So the empirical formula of that one is this one. Understand?
Yeah.
So empirical formula is with the lowest possible integer ratio. So what we got here is that, and then we just divide by the lowest number. Divide that one by itself, then you get 1. Divide this one by that one, then you get this one. Divide this one by that one, then you get this one. So it's 1, 1, 4. That's pretty good. So if you divide by, let's say you have carbon, hydrogen, oxygen. Let's say you have 0.0025 mole, and then you have 0.00735 mole, and then you have 0.0025 mole. Then what's the empirical formula for this one? Okay, well what's the lowest number of all of these? It's 0.0025, right?
Right.
So if you divide this one by itself, then you get, if you make that 1, then you get 1. If you divide this one by that, let's figure it out. That's a 0.003755 by 0.0025. So that's equal to 1.5. And then you get 1 as well, right? So is the formula CH1.50? No, gotta double that. If you double it, then you get 2, 3, 2, right?
Right.
Then
You get C2, H3, O2. Got that?
Yeah.
Yeah.
So that's the answer. So sometimes you get like decimals like that. So then you have to double, and this is the lowest possible integer ratio, isn't it?
Yeah.
That's how you do it. All right. What we need to do next is, so I'll give you some homework. So this, I'll give you this homework as, this is a balancing equation. Tomorrow we can go through stoichiometry, limiting reagents. So this is really, really important topic for year 11. This is pretty much the I guess the hardest topic for year 11 students. So we'll go through that in theoretical use. So all of that stuff we'll do tomorrow.
Yeah. So
So we've done up to 13.
Yeah.